Okay, we're going to talk about geometric sequences. Notice these sequences: 2, 4, 8, 16, all the way to the nth term. 16, 8, 4, 2, 1, 1/2, 1/4. These are all geometric sequences. Notice instead of this difference is 2, this difference is 4, this difference is 8, it's not an arithmetic sequence, right? The common thread here is what's called a common ratio. Times 2 is 2 times 2 is 4, times 2 is 8, times 2 is 16, okay? 16 times 1/2. Don't think of it as the same as dividing by 2, but 16 times 1/2 is 8, times 1/2 is 4, times 1/2 is 2, times 1/2 is 1, times 1/2 is 1/2, times 1/2 is 1/4, and so on. How do we figure out our common ratio? Very similar to figuring out the common difference. We're going to take a term and divide it by the previous term. Okay, so for this green sequence, 4 divided by 2 equals 8 divided by 4 equals 16 divided by 8, which is 2. So green sequence, common ratio 2. Blue sequence, 8 divided by 16 equals 4 divided by 8 equals 2 divided by 4 equals 1 divided by 2 equals 1/2. Okay, term divided by the preceding term. Notice this term, common ratio is less than 1, and notice how the terms get smaller and smaller and smaller, and eventually, if we're summing things up, this is where we can actually get a sum, because after a while you're pretty much adding nothing. 1 over, eventually it'll be like 1 over 5 million, and it's pretty much adding a bunch of zeros. Okay? Alright, we'll talk about that in a few slides. The recursive sequence for this is very similar. I want to get a sub 1, okay, and then basically my nth term is the ratio times the preceding term, okay? Alright, so all we need, again, is just what a sub 1 in, and this a sub 1 is, and what r is. Okay, so for this sequence, 8, 4, 2, 1, here's my recursive formula. A sub 1 equals 8. The nth term equals the preceding term times the common ratio, which is 1/2. And that is it. Very similar to what I require, what's required in arithmetic. First term, and instead of the common difference, the common ratio. Okay? A sub n equals a sub n minus 1 times the common ratio, 1/2. Alright? So that would be the recursive formula. We have to have the given. Alright? That's what we'd have for geometric sequence. Guess what? If we want to sum up all these terms, we can have a sub 1 times 1 minus r to the n over 1 minus r. Okay? So this will work if we have a finite sequence. If this goes on to infinity, we can't, obviously, we can't always sum that up if my ratio is greater than 1. Okay, so we'll talk. So the sum of 20 terms would be my first term, okay, times on this fraction of 1 minus r to the n over 1 minus r. Okay. Guess what? We have a stipulation here of r can't be 0, because if r is 0, it's basically 1 minus 0 and 1 minus 0. This is basically 1, right? So the first term times 1 is the first term. So it can't be 0, and this can't be 1 either, because this would just be 0. 1 to any power is 1, so 1 minus 1 is 0, and this whole thing is 0. Okay? And 0 times anything is 0. So r can't be 0, 1. So here's a formula for summing things up. Okay? And here's basically the sigma notation, and here I'm going to infinity, and like I said, if my common ratio is greater than 1, like 2, 3, these terms keep getting bigger and we really can't get a sum. But if we have a finite sequence, like let's say 20, we can do all the way up to here to 20 minus 1. Remember, same thing here as arithmetic. If I want the 20th term, take this back here, let me erase this. okay, if I want the 20th term, I'm going to apply that common ratio one less time. It's going to be applied 19 times. Because, just like arithmetic, for our first term, we don't apply the common ratio. So notice for the second term, I've applied the common ratio 1 time. For the third term, I've applied the common ratio 2 times. So to get the 20th term, it'll be my first term times r to the 19th power. Okay? R times R times R times R. Okay? But, alright, so it's always, we apply the common ratio one less time than the term. Okay? So for the 20th term, R to the 19th power. Okay? Alright, and you notice that is because it's, we keep going back. This is 2 times R. This is 2 times R squared. This is 2 times R cubed. Okay? Alright. Okay, if we're summing to infinity, or better yet, if we're taking, basically what I mean is, if we're taking the sum of infinite terms, we just keep going. If our common ratio is less than 1, then it's a fraction, okay? And when you multiply fractions, terms get smaller. So this geometric sum will converge on a value. We can actually sum up infinite terms, okay? Notice how I'm summing up first term, second term, third term, 1/2 plus 1/4 plus 1/8. My common ratio again is 1/2, okay? All right? 1/4 divided by 1/2 is 1/2, okay? But notice the terms keep getting smaller. 1/2 plus 1/4 plus 1/8 all the way to 1 over 128 plus 1 over 256 plus 1 over 1248. Pretty soon we'll be adding a number that's 0.00000000 if we keep going to infinity as far as the number of terms. So after a while you're adding nothing. Okay, when you start adding this and you've got this many decimals, your number's not getting any bigger, and it's going to converge on a value. Okay? So here's our formula of what the sum is going to be for infinite. Okay? This is for when we're going to infinity. Okay? It's my first term. I'm sorry, so take it back. So as we sum up infinite terms, basically taking the first term times the common ratio to, this can be infinite, this is what it'll settle on. The first term over 1 minus r. Very simple formula. And that's if your absolute value of r is less than 1. I haven't gotten into it, but you know, we can have something like this. 2 plus -4 plus 8 plus -16. Here my common ratio is a negative number. It's -2. Okay? Now that absolute value of -2 equals 2. So this value will not converge on any, the sum of this sequence as we go to infinity, if we add up infinite terms, this common ratio is not less than 1. These terms keep getting bigger and bigger, so we'll never converge on a value. Okay? But if the absolute value of my common ratio is less than 1, we will converge on this value here, okay? And this is how we determine what that value is. A sub 1 over 1 minus r. Only if absolute value of your common ratio is less than 1. It's a fraction, okay? Notice 0.9999. I'm going to prove that this value is actually 1. Notice I've got 9/10 plus 9 100ths plus 9 1,000ths plus 9 10,000ths and so on, okay? Basically plus my first term times r to the k minus 1. So my first term is 9/10, and notice the numerator doesn't change, so we're multiplying by 1. 9 times 1 is always going to be 999. My denominator, we keep going up by a place value, right? So we're multiplying 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. So my common ratio is 1/10. All right? So if I plug in 1 for my first term, 1 minus 1 is 0. Anything to the 0 power is 1 times 9/10 gets me 9/10. If I plug in 2 for the second term, 2 minus 1 is 1, which is 1/10 to the first power. So 9/10 times 1/10 is 9/100ths, times 10 square, times another 10 is to 1,000th, and so on. Okay. So my first term is 9/10, a sub 1. I want to sum up infinite terms. Okay. This should converge because why? My common ratio is less than 1. The absolute value is less than 1. Okay. All right. So the last thing, I'm going to wrap this up. So a sub 1 is 9/10, and 1 minus r, which is 1/10. 1 minus 1/10 is 9/10. So 9/10 over 9/10 equals 1. Okay. So this, we're just proving that this 0.99999, repeating is actually 1 by using our formula. Okay. So we've got this formula here. This will be the sum of an infinite sequence, infinite terms, if the common ratio is absolute value is less than 1 fraction. And we've got this, which will be the sum that we're going to use for a finite sequence, like 20, 30 terms. The first term times 1 minus r to whatever you want, 30, 40, 50, 100, over 1 minus r. R can't be 0 or 1. And we've got, remember, to find the common ratio, it's the nth term divided by the previous term. Okay, a sub n divided by a sub n minus 1. Okay, that's it. All right.